Scientists were horrified when 3I Atlas showed up and did something that no object should be able to do. Michio Kaku couldn't believe what he saw on the video. The statistics didn't make sense. The science is wrong. And what happened next shocked every space agency on Earth. Governments around the world are in a hurry. The best physicists can't believe it. And you should know why. What this thing done in our solar system will shock you to your core. This isn't a story from the future anymore. This is going on right now. On the 1st of July 2025, scientists in Chile who were using the Atlas survey system saw something strange. The Deep Random Survey Remote Telescope, which is part of the Asteroid Terrestrial Impact Last Alert System, saw a faint point of light moving across the night sky. At first, it didn't seem like anything special. Every year, astronomers make lists of thousands of these faraway things. Most of them are just pieces of rock or ice that have come in from the cold outer parts of the solar system and are following routes that have been known and mapped for decades. But just a few hours after that first observation, the crew looking at the data saw something clearly. The numbers were not adding up correctly. The thing, which was provisionally called A11PL3Z before getting its real name, was moving in a way that didn't fit the predicted patterns. It looked like it wasn't going to be pulled toward the sun by gravity. Immediately after, telescopes all around the world started to look at this strange visitor again. The Zwicky Transient Facility at the Palomar Observatory in California rapidly identified older pictures of the object in their archives, some of which were taken in mid-June. Later, amateur astronomer Sam Dean found other observations from Atlas telescopes that were made before the finding, going back to early June. Researchers looked at where it had been in the sky and figured out why it hadn't been seen before. It was moving. In front of the galactic center's thick star fields, where it would be very hard to see a faint comet against the cluttered background. By July 2nd, several observatories had corroborated what the first data had shown. This was not a normal thing in the solar system. The Canada-France-Hawaii Telescope at Mauna Kea, the Lowell Discovery Telescope in Arizona, and Chile's Deep Random Survey all saw a weak coma around the object. When a comet warms up, it generates a fuzzy cloud of gas and dust surrounding it, called a coma. The presence of this cloud showed that this was a comet and not an asteroid. Astronomers David Jewett and Jane Liu used the Nordic Optical Telescope to determine that the object was visibly active and had the hazy look that comets have. The Minor Planet Center formally reported the finding and named it 3I Atlas. This made it the third confirmed interstellar object ever found. They also gave it the name C2025N1 as a non-periodic comet. The orbit of an object is what makes it interstellar. Every planet, asteroid, and comet in our solar system moves in an elliptical course around the Sun, even if that path is quite long. Astronomers use the term eccentricity to characterize the shape of an orbit. An eccentricity of 0 means that a circle is perfect. An ellipse that is exceedingly lengthy can have an eccentricity of 0.9 or higher. But if an object has an eccentricity greater than 1, it is on a hyperbolic path, which means it won't come back around the Sun. It came from somewhere else and will eventually go back to interstellar space. NASA says that 3I Atlas has an orbital eccentricity of 6.2, which is very high. The cigar-shaped object Oumuamua, which passed through in 2017, was the first known interstellar visitor. It had an eccentricity of roughly 1.2. The second visitor, Comet 2I Borisov, was found in 2019 and came in at 3.6. There is no dispute regarding where 3I Atlas came from based on its path. The speed measurements made it seem much more special. When scientists first saw 3I Atlas, it was going about 137,000 miles per hour or 221,000 kilometers per hour. Space.com says that this made it faster than almost every comet ever documented coming into the inner solar system. That speed will only go up when it gets closer to the Sun. When things move this rapidly on hyperbolic paths, they are basically cutting through the solar system instead of slowly orbiting it. 3I Atlas came very close to the orbital plane where Earth and the other planets go around the Sun. Most things that come from interstellar space come in at strange angles, cutting abruptly above or below what astronomers call the ecliptic plane. But orbital modelers say that 3I Atlas passed at an angle of around 5 degrees from the ecliptic. This kind of alignment is quite rare, with some estimates saying that the chances of it happening are only 2 in 1,000. Around the 30th of October 2025, the comet will reach its closest point to the Sun, called perihelion. At that point, it will be around 1.4 astronomical units from the Sun and just inside the orbit of Mars. The distance from Earth to the Sun, which is about 93 million miles, is 1 astronomical unit. In mid-December, the 3I Atlas will come the closest to Earth, around 270 million kilometers, 170 million miles away. NASA said that the comet poses no threat to Earth and will stay safely far away when it passes by. What truly got scientists interested, though, was what happened as 3I Atlas got closer to Earth. NASA's Transiting Exoplanet Survey satellite saw signs of activity on the comet as early as the 7th of May 2025, when it was still around 6.4 astronomical units from the Sun. This was very strange. Most comets don't start to form their characteristic comas until they travel a lot closer to the Sun, usually within 5 astronomical units of Jupiter's orbit. The Sun's rays need to be strong enough to melt the frozen ice on the comet's surface and transform it into gas. The fact that 3I Atlas was active from such a long distance suggested that it was made of something very unstable, something that would turn into gas even with only a little heat. Several observatories confirmed the early activity. By the beginning of July, high-resolution pictures from the Gran Telescopio Canarias showed that the coma around 3I Atlas had grown to around 26,400 by 24,700 kilometers in diameter, which is about twice the size of Earth. Before the discovery, the Vera C. Rubin Observatory recorded how the coma grew from 13,040 kilometers on June 21 to 18,760 kilometers on July 2. The growth was consistent and never stopped, just what you would expect from a comet getting warmer as it got closer to the Sun. Spectroscopic investigation showed anything interesting about the coma's makeup. The dust particles that were coming out looked to be very big, with a radius of a few micrometers, and they were clearly reddish in color. Astronomers have seen this reddish color in some asteroids and in the last interstellar comet, 2I Borisov. Tholins are organic compounds that arise when ultraviolet radiation breaks down simpler molecules over a lengthy period of time. This is probably what gives the hue. On July 21st, NASA's Hubble Space Telescope took close-up pictures of 3I Atlas while it was roughly 277 million miles from Earth. The pictures showed a teardrop-shaped cloud of dust coming from the comet's nucleus, along with signs that a tail was starting to emerge. The surrounding stars looked like stripes in the exposure because Hubble was following the comet as it moved quickly. Astronomers were able to start figuring out how big the comet's nucleus is, which is the solid frozen core at its heart, thanks to these observations. As of late August, the nucleus's diameter was thought to be no more than 3.5 miles, 5.6 kilometers, but it could be much smaller, maybe even as little as 440 meters across. It's hard to tell the difference between the solid nucleus and the coma from so far out, which is why there is doubt. In those first several weeks, it wasn't apparent what 3I Atlas was comprised of, or why it was acting so differently from other comets. The fact that it became active so distant from the Sun suggested that it was made up of a lot of very unstable components. Jacqueline McCleary, an assistant professor of physics at Northeastern University, told reporters that dry ice, or carbon dioxide ice, melts far more easily than water ice. If frozen carbon dioxide blanketed the surface of the comet, that would explain the early activity. The answer would shortly come from NASA's James Webb Space Telescope, which has excellent infrared tools. Webb's observations showed that carbon dioxide made up most of 3I Atlas, with a ratio of around 8:1 between carbon dioxide and water ice. This is one of the highest ratios ever reported for a comet, from our solar system or anywhere else. It indicated that 3I Atlas originated in settings markedly distinct from those that generated the comets indigenous to our solar system. Finding a composition high in carbon dioxide was scientifically important, since it gave us a glimpse into how other planetary systems originate. Researchers say that pure material from other solar systems is really valuable for figuring out how different conditions lead to different results. Our solar system made it possible for life to start on Earth, but how frequent or rare are comparable conditions throughout the rest of the galaxy? Scientists can improve their models of how planets develop and compare our cosmic neighborhood to others by studying interstellar visitors like 3I Atlas. It asks basic questions concerning whether our solar system is normal or special. As the weeks passed by and additional telescopes looked at this visitor from space, scientists quickly got to work gathering as much information as they could before the comet's short period of sight ended. There was a strong sense of urgency because chances like these don't come around very often, and every observation could teach us something new about the vast, mostly unexplored areas between the stars. As the astronomy world got ready to see 3I Atlas pass through our solar system for a short time, the most powerful telescope ever built oriented its golden mirrors toward the visitor from space. The James Webb Space Telescope used its near-infrared spectrograph to look at the comet on the 6th of August 2025. This tool was made to study the chemical makeup of faraway things by analyzing the light they give off. The observation period only lasted 18 minutes, from 11:02 to 11:20 Universal Time, but Webb's camera caught something that would change our knowledge of this strange object forever. Martin Cordner of NASA's Goddard Space Flight Center and the Catholic University of America organized a carefully designed campaign that included the observations. The team employed Webb's integral field unit, which makes an array of 30 by 30 spectra that encompass wavelengths from 0.6 to 5.3 micrometers. This range covers the near-infrared part of the electromagnetic spectrum, which is great for finding the heat signatures of gases that are warming up in the comet's coma. When we looked at it, 3I, Atlas was 3.32 astronomical units away from the Sun, which is well within Jupiter's orbit but yet far enough away that its activity should have been rather low, according to what we know. The data showed something amazing. The spectral pictures showed that the coma around 3I, Atlas, was mostly made up of carbon dioxide, which had never been seen before. The team figured out that there was around 7.6 parts carbon dioxide to 1 part water in the coma, with a margin of error of plus or minus 0.3. The published results show that this is one of the greatest ratios of carbon dioxide to water ever found in a comet. The researchers found that this ratio was 4.5 standard deviations, higher than what is usually seen in long-period comets and Jupiter family comets from our own solar system. A variance of 4.5 standard deviations means something really unusual, not just a small change within what is normal. The Webb observations also found other things in the coma. There was water, but not as much as there was carbon dioxide. Astronomers usually see comets with a carbon monoxide to water ratio of approximately 1.4, which is more like what they saw in this case. The scientists also said they might have found carbonyl sulfide, a more complicated chemical, along with water ice crystals and dust particles. The imaging showed that the outgassing wasn't the same all over the comet's surface, which is interesting. There was more activity on the side facing the Sun, which is what you would expect because solar radiation heats that hemisphere more strongly. The statistics made it evident that this pattern was not symmetrical, with more dust and gas coming from the side facing the Sun. NASA's SPIREX mission also made more observations of 3I, Atlas between August 8 and 12, when the comet was at a comparable distance from the Sun. The spectrophotometer for the history of the universe, epoch of reionization, and ICE's explorer, SPHEREX, was able to perform multispectral observations that added to what Webb had already seen. The SPHEREX data showed a huge cloud of carbon dioxide that stretched at least 348,000 kilometers from the nucleus. It could only be seen in near-infrared wavelengths. The mission team said that carbon dioxide was losing mass at a rate of about 70 kilograms per second. On the other hand, there was no large water cloud, and the water mass loss rate could only be 4.5 kilos per second at most. This made it even more clear that carbon dioxide was the main cause of activity for this comet. Researchers understandably wondered why 3I, Atlas, had such a unique makeup. Based on the facts, a number of possible hypotheses have been put forward. One theory is that the comet formed in a part of its parent star system that was very cold, much below what astronomers call the carbon dioxide ice line. This is how far away from a star the temperature gets low enough for carbon dioxide to turn into solid ice. This line is far farther out in our solar system than the water ice line. This means that an object growing beyond it would naturally have more frozen carbon dioxide than water. If 3I, Atlas formed in such a remote, cold area, and then spent billions of years in the cold of interstellar space, it would make sense that it is made up of a lot of carbon dioxide. Another reason could be exposure to radiation. Researchers said that the high amount of carbon dioxide could mean that the comet's ices were exposed to far more ultraviolet light or cosmic rays than comets in our solar system usually are. Over time, strong radiation can change the chemical makeup of ices, which could cause water to disappear while keeping carbon dioxide or other volatile substances. This means that either the area near 3I, Atlas's parent star, was quite harsh, or the comet spent a long time in areas of interstellar space where radiation levels are very high. Some scientists think that 3I, Atlas, might be far older than our solar system, possibly more than 7 billion years old, if it came from the thick disk of the Milky Way galaxy, instead of the narrow disk where our Sun is located. This old object would have been exposed to radiation for a very long time. The isotopic makeup of the carbon in 3I, Atlas also gave us some hints. The proportion of carbon-12 to carbon-13, the two stable isotopes of carbon, was determined to be largely analogous to that found on Earth and within our solar system. This means that even though it came from a strange place, the basic chemical processes that made the carbon in 3I, Atlas, were not very different from the ones that made our Sun and planets. It shows that there is a certain universality in how elements are made and spread throughout the galaxy, even though the conditions and results can be very different from one star system to the next. The Webb findings were especially useful because they were compared to the only other interstellar comet that had been analyzed in depth. Astronomers were able to study the coma of 2I Borisov when it passed through the solar system in 2019. They found that it had a rather high carbon monoxide to water ratio. It looks like each interstellar visitor has its own chemical signature, which shows how different the conditions are for forming planetary systems in different parts of the galaxy. Oumuamua, the first interstellar object, didn't make a coma that could be seen at all during its 2017 flyby. It was only seen as it was exiting the solar system, which made it impossible to do a complete chemical study. With 3I, Atlas, scientists finally had the chance to do precise spectroscopic observations of an active interstellar comet while it was still coming in and brilliant enough to investigate in detail. The observations had big effects on our knowledge of how planets arise outside of our solar system. Researchers who have looked at the data say that interstellar objects are the only physical samples from other star systems that people have been able to look at directly. We have found thousands of exoplanets using indirect methods like transit observations and radial velocity measurements, but we have never been able to study material from those systems in depth. Comets like 3I, Atlas bring back clean material from the farthest parts of their parent systems, where it has been frozen for billions of years. Scientists can test their ideas about how different conditions affect the chemical results of planet formation by looking at their composition. The time to see 3I, Atlas was short and getting shorter. By the end of September, the comet would be too close to the Sun for telescopes on Earth to see it safely. At the end of October, its perihelion passage would put it on the other side of the Sun from Earth, making it difficult to see during that important time. In early October, some spacecraft that were going around Mars were supposed to try to take pictures of the comet as it passed close to the red planet. However, these pictures would only give a small amount of information. When 3I, Atlas eventually came back into view in December, it would be speeding out from the inner solar system, and a lot of the unstable material it had been losing would be gone. Because the observing window was so short, every telescope that could examine the comet had to be used, and each observation added to the mystery of where this visitor originated from, and what its journey through the galaxy was like. Astronomers kept watching 3I, Atlas, throughout the summer and into the fall of 2025. At the same time, defense and security groups around the world were secretly coming up with a reaction. Military analysts who keep an eye on space for hazards to satellites and other orbiting equipment had observed the comet's very fast speed and strange path. 3I, Atlas was the kind of fast-moving object that current detection and tracking systems have trouble with because it traveled at about 130,000 miles per hour. For networks that were originally built to keep an eye on satellites or find incoming missiles, these speeds make reaction times much shorter, leaving little room for mistakes or delays in any response situation. The object's strange route across the solar system made it even harder to track. Asteroids move in regular elliptical orbits around the Sun, but 3I, Atlas was moving in a hyperbolic path that didn't fit with standard prediction models. Defense organizations that use complex algorithms to estimate where things would be in space had to change their systems to deal with this kind of unpredictable visitor. The comet's path was even more interesting to track because it came relatively close to the plane where Earth and other planets orbit, rather than coming from far above or below like most interstellar objects do. The main goal of military space surveillance systems is to keep an eye on things in the solar system, especially those that are in Earth orbit or coming from the asteroid belt. The rapid arrival of a fast-moving visitor from another star showed that these early warning networks might not be as strong as they could be. Analysts that look at space defense readiness say that objects flying at such high speeds could briefly avoid detection if they come from particular angles or during gaps in coverage. 3I, Atlas itself didn't represent a threat to Earth, as it was roughly 270 million kilometers away at its closest point in December. However, its presence was a real-world test of how successfully current systems can find and monitor visitors from outside the solar system. The effects go beyond just finding things. Objects moving quickly through the inner solar system could hit satellites, space stations, or military reconnaissance equipment that are in orbit. A single hit from even a small piece might cause huge problems for defense or navigation networks that modern military operations rely on. The event showed that we need better ways to avoid collisions, stronger protection for important spacecraft, and faster ways to track orbits. Experts said that these kinds of situations might mess up communications, GPS, navigation, and intelligence gathering, all of which are important parts of modern military infrastructure. The International Asteroid Warning Network, a group of countries that the United Nations supports that keeps an eye on rocks that are close to Earth, made a big announcement in late October 2025. The group officially started a coordinated observation campaign just for 3I Atlas. The Minor Planet Center at the Smithsonian Astrophysical Observatory sent out the formal circular on October 21st. It said that the campaign would run from November 27, 2025 to January 27, 2026. The declared purpose was to get accurate measurements of the comet's position, But this was hard because the gas and dust around it made it hard to see its true center and made it harder to figure out its path. NASA officially added 3I Atlas to the International Asteroid Warning Network's protocols. This was the first time an interstellar object had been added to the network's tracking list. The organization stressed that the comet would not hit Earth, but adding it to planetary defense measures was a proactive step in worldwide astronomical monitoring. While the object was still visible, it would allow astronomers all across the world to improve their predictions of its path and their methods of observation. As part of the campaign, there was a mandatory workshop on November 10th, followed by 3 phone calls to make sure that all observatories used the same methods for taking measurements and to see how well the worldwide community could track objects for planetary defense objectives. A lot of people outside of the scientific community were interested in the timing and scope of this effort. Some others said that it showed an unprecedented level of collaboration and intensity for something that was apparently not a danger. The campaign's goal was to improve astrometry, which is the exact measurement of the positions and movements of celestial objects. This was framed as a training exercise to get people ready for possible future dangers. The IAWN said that this project will let the observing community test and improve novel approaches on a single target. However, it is hard to calculate credible orbits without correct positional data. The fact that observatories from many continents, including ones in Hawaii, Chile, and Europe, were involved showed how big the concerted effort was. Defense analysts said that the quick mobilization around 3I Atlas showed how important it is for countries to work together to keep an eye on space. To make sure that fast-moving objects are monitored and understood correctly, countries need to share data in real time. Without coordination, there is a chance that natural events could be seen as possible threats, which could cause misunderstanding or unwarranted worry among defense organizations. The 3I Atlas instance showed how global networks should behave when something unexpected happens in space. The effort was also a big commitment of observational resources during a very important time. The comet's perihelion transit on October 30th put it on the other side of the Sun from Earth, making it impossible to see for a short time. The observing community would have only a short time to collect data once the comet reappeared in early December, when it would have been too dark to see as it moved away from the Sun. The December viewing window, which coincided with the apex of the IAWN campaign, represented the final opportunity to examine 3I Atlas in detail before to its permanent exit from the solar system. There were practical reasons for the increased focus, even though the official pronouncements talked about scientific opportunity and planetary defense training. Telescopes that were following 3I Atlas have seen some strange things that needed to be looked into more closely. Astronomers at the Nordic Optical Telescope in the Canary Islands saw that the comet had what they dubbed a anti-tail earlier on its trip to the Sun. This meant that particles seemed to be streaming toward the Sun instead of away from it. This event wasn't completely new for comets, but it was strange enough to need more research. By September, the tail had flipped back to a more normal position, flowing away from the Sun as it should have. To figure out what caused this change, we needed exact measurements and coordinated observations from several places. The larger picture of space. Security also had an effect on how people reacted to 3I Atlas. As more countries get better at doing things in space and as business in orbit increases, it becomes more and more important to keep an eye on possible dangers. An interstellar object traversing the inner solar system offers a distinctive opportunity to evaluate detection networks, communication protocols, and analytical methodologies in authentic conditions. By a defense point of view, the lessons learned by tracking 3I Atlas should help us respond better to future objects, whether they are natural or possibly dangerous. The exercise improved international cooperation in precision tracking and showed that the worldwide astronomy community can swiftly go to work when needed. During this time, official messages from space agencies and groups that protect planets stayed the same. 3I Atlas was a natural comet that didn't pose a threat to Earth. The coordinated observations were a normal part of scientific practice and a great way to learn. The focus stayed on the rare chance to study material from another star system and improve the ways we find strange things. Still, the size and quickness of the response showed how seriously space agencies and defense organizations take the problem of keeping an eye on and figuring out what unexpected visitors from deep space are doing. As 3I Atlas got closer to the Sun in late October 2025, astronomers started to look for evidence of what happens to comets when they become very hot from the Sun. The comet would be 1.36 astronomical units away from the Sun on October 29th, which would put it between the orbits of Earth and Mars. When the Sun is this close, its radiation is strong enough to quickly heat the nucleus, which makes volatile substances like carbon dioxide and water ice sublimate faster. This process can cause internal pressures and heat strains that can sometimes cause catastrophic breakage occurrences. The last intergalactic visitor made it Obvious what to do. In March 2020, about 3 months after its perihelion, Comet 2I, Borisov, which traveled through the solar system in 2019, had broken up. The Hubble Space Telescope saw the nucleus break apart into at least two separate pieces that were around 180 kilometers apart. The nucleus broke apart when Borisov was roughly 2 astronomical units from the Sun. This was because volatile evaporation and maybe rotational stress made the structure weak. That incident taught us a lot about what interstellar comets are made of and how they are put together. It showed that they can be loosely consolidated things instead of solid blocks of ice and rock. There was a lot of talk about the prospect of fragmentation in scientific papers and observational planning documents for 3I, Atlas. In his study, Avi Loeb, an astrophysicist at Harvard, said that comets can break apart in a number of ways. The sun heating the ice is the most typical reason. When ice sublimates, it makes jets of gas that can behave like uneven thrusters, which can spin up the nucleus or make it weaker. Gravitational tides can also break up comets when they get too close to big objects. For example, in 1994, pieces of comet Shoemaker-Levy 9 slammed into Jupiter after being pulled apart by that planet's gravity. Another way for comets to break up is through rotational stress. Some comets spin so fast that the forces of centrifugal force are stronger than the strength of their structure. The European Space Agency's Rosetta mission got a close-up look at Comet 67P, Churyumov-Gerasimenko, and studies of it and other comets have showed that many of them are loosely held together, entities made up of smaller fragments that came together slowly. This form of construction, which is sometimes called a rubble pile, makes them very likely to break apart when they are under stress. The fact that 3I, Atlas, was mostly made up of very unstable carbon dioxide ice made it seem like it could be especially easy to break apart when it got hotter around perihelion, but it was still very hard to guess if and when fragmentation would happen without knowing the nucleus's exact internal structure and material strength. From August to September 2025, it was clear that 3I, Atlas, had stayed at the same brightness and activity levels, with no abrupt outbursts or hints of large structural changes. Between July and September, the Nordic Optical Telescope took pictures that showed the tail changing from an odd anti-tail shape, where material seemed to flow toward the sun, to a more normal tail shape, where it pointed away from the light. As the comet moved in relation to Earth and the sun, this change in direction modified how we saw the outgassing jets. The pictures also showed jets of dust and ice coming out of the nucleus, which is a natural part of a comet's activity that would get stronger as perihelion got closer. The perihelion passage itself was hard to see in several ways. From Earth's point of view, 3I, Atlas, went behind the sun, making it impossible for ground-based telescopes to follow it directly. The sun's glare would hide the comet for much of late October and all of November, making it difficult to see any changes that might happen during this important time. But spacecraft in other parts of the solar system could watch. NASA's Mars Reconnaissance Orbiter and the European Space Agency's Mars Express and ExoMars Trace Gas Orbiter were all in orbit around Mars to watch the comet as it got closest to the planet on October 3rd. At that time, it was about 30 million kilometers from Mars. These spacecraft has high-resolution cameras and spectrometers on board that are usually used to look at the surface of Mars. Even though they weren't designed to see faraway comets, the fact that they were so close gave them a chance to get data that couldn't be gotten from Earth. The instruments would try to take pictures of the coma and measure the light spectrum from the comet, but they would only be able to do this if 3I, Atlas, stayed bright enough to be seen. The JUICE mission from the European Space Agency was on its way to Jupiter through the inner solar system. It was expected to have an even better view in November, when the comet would be very active after perihelion. But JUICE was on the other side of the sun from Earth and was using its main antenna as a heat shield, so the data from those observations wouldn't be sent back until February 2026. When 3I Atlas eventually reappeared from behind the sun in early December 2025, scientists would instantly look for any changes in its shape or structure. If fragmentation had happened during the perihelion passage, we would see numerous nuclei moving together, each with its own coma. Depending on when the breakage happened and how much speed difference there was between the parts, the components would be separated by hundreds to thousands of kilometers. Telescope photos would show extended structures of dust trails coming from the broken pieces. The International Asteroid Warning Network's coordinated observation campaign, which will start on November 27, was planned to take place during this important time after perihelion. Telescopes all across the world, including big ones like the Canada, France, Hawaii Telescope and the Vera C. Rubin Observatory, would work to get exact measurements of the comet's position and shape. If several pieces were found, following their paths would provide us useful information about the forces that triggered the breakup and the physical features of the original nucleus. The campaign was a unique chance to see how an item in space reacts to solar heating in real time. The perihelion crossing would change the comet's appearance and activity, no matter if it broke up or not. 3i, Atlas would start its voyage back out of the inner solar system after it got as close to the Sun as it could. It would pass Venus in early November and then keep going outward past Earth's orbit. In March 2026, the comet would come within roughly 54 million kilometers of Jupiter, which might let NASA's Juno probe see how gravity works. As the comet traveled away from the Sun and its ices sublimated more slowly, it would gradually disappear. By the middle of 2026, it would probably be too faint to see clearly, and it would fade back into the black abyss between stars whence it came from, taking with it any secrets that were still concealed in its ancient ice.